This time around, we're just trying to make an extension to what we discussed earlier, which was about stress. One thing we didn't discuss was if a direct stress is acting longitudinally along the axis of your material, what happens to the transverse section? What happens to the plane at 90 degrees to where the force is acting? Perhaps we are trying to pull apart a material. What happens to that? So that's where this ratio comes in, which is known as Poisson's ratio in strength of materials. And we'll take time to discuss what it is. Now, one thing you realize is that when you're compressing a material, when you're trying to squeeze the material together, the length is going to reduce. But unfortunately, the width will increase. After all, how do you account for that material which was trapped, which you are trying to squeeze together? In a similar sense, if you are pulling a material apart, extending it, where is that length coming from? It is because the diameter is also reducing. The cross-section is reducing, whereas the length is increasing. So it's like opposite. Whereas on the one end, you can have a material where when you're pulling it apart like that, in tension, then the length is actually increasing like that. However, unfortunately, that diameter, the cross-section, is going down, it's reducing. So they work in the opposite. So that is where we review Poisson's ratio. And according to this ratio, it brings together those two strains together. We have what we are calling the primary strain, which is the strain where the force is acting directly and tampering with the material. Here now, I'll give an example of a material that is being squeezed. So if you are pushing this material together like this, it means this length itself, this length is going to reduce because you are compressing it. The length will reduce and it will end up, of course, being like that. But unfortunately, for the width, it's going to increase. So you have something like that because that length, that cross-section will have some increment, whereas the length will reduce. So they just compensate each other. That is your force there. Now, to account for this, we always say that because Poisson's ratio, you cannot have a number like 1. It will be that secondary strain divided by the primary strain. So you will notice those two alternating like that. So this one, at 90 degrees to where this is acting, the strain that is acting there is the one we are calling the secondary strain, whereas the strain coming as a result of this direct stress, that is the primary strain, the one we just from calculating. Now, what is Poisson's ratio, having discussed that? So here we've already said that is the ratio between the lateral strain as well as the linear strain. In other words, we're saying this is the ratio between the secondary and the primary strain. I usually prefer this one because it's smarter and faster. Now, look at our formula. This is Poisson's ratio, negative lateral over linear. Why is it carrying a negative? This is where I took time to explain that the way this behaves is that when one is positive, the other one will definitely be negative. So you're basically having one strain being negative, the other one is positive. If this other linear is positive, the other one, if the primary is positive, it means the secondary will be negative, just like that. So that's why the whole ratio carries a negative like that. So this is what we're discussing, meaning that when you have been given a situation, your starting point will usually be this, because these are the parameters you'll be provided with. Those are the dimensions you'll be given as to what is leading to the primary strain. In some cases, you could also be provided with what is helping you to find the secondary strain. Then later on, you also get what is helping you for the primary. Then you find Poisson's ratio. or Poisson's ratio has been provided, then you need to find one of them, then escalating to calculating for those changes in either length, width, thickness, name it. So we just pick up one example to ensure that we illustrate this and explain it in full. So here is a steel bar whose cross section is 20 millimeters by 30 millimeters, length 50 centimeters. Then the tensile force of 2 kilonewtons is acting on it. Young's modulus is 2 gigapascals, and we have Poisson's ratio. So as our usual favorite, here we are saying that this is 20 by 30, like that. Then the length is there. The length of this is 50 centimeters. And here is where you see the importance of being very careful with the units, because the units have been combined. Here you're using millimeters, there you're using centimeters. So we'll have to be careful. Now look at our information. First of all, here we convert them like we had earlier. This side, 20, the other one, 30, the other one, 50 centimeter. So this 20 is 0.02 because you divide this by 1,000 to convert it to meters. The same thing with this, divide by 1,000, you have 0.03. Then if you take this one, the length, you simply divide it by 100 because this is in centimeters. Converting centimeters to meters, that's what we do. So 50 centimeters divided by 100 or multiplied by 10 power negative 2. The same as here, you can either divide by 1,000 or multiply this by 10 to the power negative 3. Once you've done that, then you're ready now to just plant the numbers where they are. So our area, 0.02 by 0.03, we have 6 times 10 power negative 4, which is like 0.0006 square meters. Original length, 0.5. Force is 2 kilonewtons. This is a tensile load. It's a pulling force, pulling the material apart. So it's positive. So F is 2,000 newtons because it's kilonewtons. So converting, that's what we have. Young's modulus is 200 gigapascals. So the giga represents 10 raised to power 9. So you write 200 times 10 raised to power 9. You've converted, and it can now remain in pascals. All is well. Poisson's ratio, 0.4. So there you have it as our 0.4. So what do we need to find? We are taught to find the change in length, width, and thickness. This is the width, that is the thickness, and this is the length. So where are we starting from? Of course, the width, like we had said, that's the first one, the first part. Then the thickness is this one. And of course, the length is 0.5. First things first, let's find the stress. Stress, the direct stress is force over area. So the force was 2,000 newtons. The area was 6 by 10 power negative 4. From your calculator, you enter this, you get your stress, which is 3,333,333.333. Then we can now make progress from there. What about the primary strain? To get the primary strain, we involve Young's modulus, because here we're saying strain is stress over Young's modulus. Our stress is this one we just found. Young's modulus is 200 by 10 power 9. So when you enter these again, you get 1.66666 by 10 power negative 5. So we shorten it as 1.667 times 10 raised to power negative 5. As usual, strain, no units. So this one we found is our primary strain, which is going to review what the secondary strain is. But we don't have to rush there. First, the question was asking us to find the change in length. Remember that when this force is applied on the material, the primary part that it is affecting, because it's applied longitudinally, is this same length, because we're saying like that. Sorry, let's try to be a bit, okay. There. So when this force is applied, what is affected directly, primarily, is the length. The other ones will be affected in the secondary sense later on or after. So then we can now apply that formula for strain, which is change in length over original length. And we will use this same value we have here. So we'll say, make change in length the subject. You have original length multiplied by the primary strain. Original length multiplied by our primary strain. So then our original length was 50 centimeters. Converted to meters is 0.5. The primary strain, this is the one we just from calculating, 1.667 times 10 raised to power negative 5. So then our answer is 8.335 times 10 power negative 6 meters. Okay, so it means that our change in length is done. But then if the question had requested us to find the final length, it means we have to add this to the original. But for now, all we need is the change. To find now the change in thickness and width, we will need the secondary strain. Now the secondary strain, to get it, we have to go through Poisson's ratio. So Poisson's ratio, we said, that's the ratio between secondary and primary strain. So with this, our Poisson's ratio was, or rather we make secondary strain the subject, it will be secondary strain, take care of the negative when you cross multiply, you have mu multiplied by primary strain. So there we can divide through by the negative. So the this Poisson's ratio is 0.4 multiplied by the secondary strain. So what we have now is negative 6.667 times 10 raised to power negative 6. So now that you have your secondary strain, you can now review the formula for secondary strain because it applies to both the width as well as the thickness. The thickness. So in this case, we start with the width. Secondary strain is equal to change in width divided by original width. Secondary strain equals change in width divided by the original width. So if I make change in width the subject of the formula, this is what I will have. It will be original width times the secondary strain, basically like we just cross multiplying. Then being our original width, it was 0.02 meters. Secondary strain is this number here, negative 6.667 times 10 power negative 6. So the product from this workout is negative 1.333 times 10 raised to power negative 7 in meters. So that is how much the width is going to change. Whereas the length is increasing, the width will be reducing by this much at that point when that force is applied in that manner. This is the same thing we are going to do even for the thickness because both the thickness and the width are in the cross section. We're saying that here we have, this is the thickness and that is the width. So both of them are being handled by the same strain because it's along the cross-section of the material. The only different one is the length, which we found on its own. It's the one that is making use of the primary strain. So both of these, width and the thickness, they are making use of the secondary strain. So let's go then to the thickness. Of course, here we're interpreting, we're saying this is a change in width. The negative is indicating that the width is decreasing. The width is reducing. That width is being compressed. Secondary strain is change in thickness over original thickness. Same thing, we make change in thickness the subject of the formula. We'll have original thickness multiplied by the secondary strain. Original thickness by secondary strain. So then our original thickness is 0.03. Secondary strain, negative 6.667 times 10 power negative 6. And then that's what we get from working out this one, negative 2 by 10 power negative 7. If you use this number the way it is, it will give you something very close to 2. But if you use the number the way it is appearing on your calculator, this is the result you get. Negative 2 times 10 raised to power negative 7. Again, this negative in front here is trying to tell us that even the thickness is also being reduced, for the simple reason that the length is actually increasing. The opposite is where when we are squeezing the material, compressing the material, then the original, it could be the length, the primary one that is receiving the force, is going to increase, or rather it's going to reduce, whereas the thickness or the cross-section will be increasing. So in this case, this is how things play out. All right, so that is how you handle Poisson's ratio. The analysis can vary depending on what we have. And again, we're just emphasizing there about why we have a negative. Again, this also is coming with an exercise. You take time to go through and answer the exercise. Where queries come, please feel free to reach out to me. Or you can also post a comment in the comment section.